This is Module 6. We're starting on Lesson 4 in the book, but this is Lesson 1 that we're teaching for Module 6. Okay, we're talking about increasing and decreasing functions. Let's start right here. This is a linear function whose graph has a positive slope is an increasing function. It would look like this. See how it's going up? This is an increasing function. If it has a negative slope, it's a decreasing function. Okay? It's going down, so it's decreasing. A linear function whose graph has zero slope is says to be constant. We're just going to say that it's got a zero slope. Okay? It doesn't change. Because it gets really confusing when you start talking about a constant rate of change and a constant function. This one just has zero slope. Okay? So, down here, they've given you 4 scenarios, and they have given you graphs. This is on page 37 of your workbook and 38. There's 4 scenarios here, and they want you to plug them in, or want you to match them to their graphs. So let's look at this first one. Okay, we're talking about a bathtub is filled at a constant rate of 1.75 gallons per minute. A bathtub is drained. So if it's filled, it's going to be going up. It's going to be increasing, right? If it's drained, volume's going to be going down. A bathtub contains 2.5 gallons of water. A bathtub is filled at a constant rate of 2.5 gallons per minute. So this one's going up, it's increasing in volume. This one is staying completely the same. So here we've got amount of water in the tub, time. This one here is not going to change. It stays exactly where it is. Notice it is at 2.5 gallons, and it doesn't change from that 2.5 gallons at all over time. So this is just a bathtub contains 2.5 gallons of water. Why? The water volume does not change. Oops, water volume, V-O-L-U, volume does not change. Okay. Let's look at the others. This one is going down. So we can say that a bathtub is drained. So this one deals with the bathtub being drained. This is scenario B. Bathtub is being drained. Water level goes down. When bathtub is drained. Okay. Now I've got 2 where the water level is going up. What can we see a difference in those? Let's see. We've already done the constant rate one. We've already done drained. Both of them are being filled. This is at 1.75 gallons per minute. This is at 2.5 gallons per minute. So this one is going up faster. D is going up faster. That would be here. See how this one's going up at a sharper rate than the other one? Okay, so this is scenario D. Explanation. Water's increasing at a faster rate. Water volume is increasing at a faster rate than in the scenario shown below. Okay, and with the water level increasing slowly, that would be A. Okay. Okay, read through each of the scenarios and sketch a graph of a function that models the situation. A messenger service charges a flat rate of $4.95, to deliver a package regardless of the distance to the destination. Okay, $4.95. If there's 0 distance, $4.95. That's close to $5, about halfway between 4 and 6. And no matter the distance, it does not change at all. So all you're looking at is a straight line, something that has no change. It is just constant. Okay. Let's look at this one. At sea level, the air that surrounds us presses down on our bodies at 14.7 pounds per square inch. It's about 15, isn't it? For every 10 meters that you dive under the water, that pressure increases by 14.7 pounds per square inch. So that's 14.7 psi per 10 meters, right? Okay, so where do we start? At zero depth, that's at sea level, it's about 15, so that's close to the 20. And then each 10 meters is going up another 15, okay? Be about 30, be about 45, okay, somewhere in here, okay? And it's going up, so you're talking about a line that looks like this. This is increasing. This is an increasing function. Number 3 on the next page, there's 3 scenarios here. You see, you're looking at, you're looking at the number of smartphones that have been shipped to a resale store over 50 days' time. Between 0 and about what, 20 days, they ship over 2,000, right? Then for these few days in here, none are shipped, right? No change. And then from here to here, they ship more, but it looks like they're shipping in a smaller rate, right? Okay, so here's our scenarios. Half the factory workers went on strike and not enough smartphones were produced for normal shipments. Here are others on the next page. The production schedule was normal and smartphones were shipped to the retail store at a constant rate, or a defective electronic chip was found and the factory had to shut down, so no smartphones were shipped. Well, let's see where none were shipped. None were shipped would be B, wouldn't it? Okay. This is where they're shipped at a normal rate, okay? Here would be A, normal rate. How do I know it's not C? Because it says here, half the factory workers went on strike and not enough phones were produced for normal shipments. So that would mean fewer would be shipped, right? So there's C. Okay, let's look at the bottom one. The relationship between Jameson's account balance, see that's it on the y-axis, and time on the x-axis can be modeled below. Write a story that models the situation. Well, what does Jameson start at? He starts at about somewhere really close to this 60. That'd be about 50 there, so maybe 55. Jameson's account has about $55 in it. Six days later, let's see what happens after 6 days. After 6 days, what's going up? The account balance is going up. Is it going up all in one day? No, this is about at what? Let's see, about where that is. Oh, that's about at 9 days, right? So between 6 and 9 days, over 3 days, it's going up at a constant rate. After 6 days, Jameson starts to deposit the same amount of money each day for how many days? For how many days? Let's see. From 6 to 9, so for 3 days, right? For 3 days, okay? Then Jameson starts to spend money from what? 9 to 14. So 14 minus 9, that would be what? The next 5 days. Then for the next 5 days, Jameson spends what? The same amount of money each day, right? Okay, when is the function represented by the graph increasing? Okay, that would be from 6 days to 9 days, right? 6 to 9 days. What's happening in that time frame? He is depositing money, right? When is it decreasing? From 9 days to 14 days, right? You see it's going down in that time frame from 9 to 14. From 9 days to 14 days. How does that relate to the story? He is spending money, right? Okay. Now, let's look at lesson 5 here, increasing and decreasing functions, right? Not all real world situations can be modeled by a linear function. This one is linear and it's increasing. See how it forms a straight line? This one says that Aleph is running at a constant rate on a flat paved road. So see, his run, the distance that he travels over time is the same as he runs, right? This one says Shannon is running on a flat rocky trail that eventually rises up a steep mountain. The graph below shows the total distance she covers with respect to time. So she's moving faster earlier in her thing, and then she slows down as she goes up the mountain, right? This is a nonlinear function, although it is increasing. Okay, on the next page it says, in your own words, describe what is happening as Aleph is running during the following intervals of time. From 0 to 15 minutes. Let's see, Aleph, from 0 to 15 minutes. Here's 0 minutes. Here's 15. Okay, so Aleph is going, let's look for her rate of change. The change in Y over change in X. Aleph is going 2 miles, okay, over that 15 minutes, correct? So from 0 to 15 minutes, he's going up 2 miles per 15 minutes. Let's look at the 15 to 30 minute time frame, see what's happening there. From 15 to 30 minutes, this would be 30 minutes. Okay, so we'd start at 15 and we go over here to 30. At this time frame, he's going from 2 to 4, so he's going up 2 miles in 15 minutes. Okay, so again, our rate is 2 miles per 15 minutes. All right, the slopes are the rate of change is the same that whole time. Now let's do 30 to 45 minutes. From 30 to 45 minutes, here's 45. So we go from 4 up to 6. It's going up 2 miles over 15 minutes. All right. Let's go over here. That means 2 miles per 15 minutes. The rate is exactly the same there. And then let's do this last one. This last time frame from there to 60 minutes. I'm going from 6 to 8, so that's up 2 miles over the 15 minutes. The rate's still the same. We're still going, she's still running 2 miles in that 15-minute interval, right? Notice the rate is the same on all of these, 2 miles per 15 minutes. Everywhere along this, it is exactly the same. If the rate is the same between any set of points, then what we have is a linear equation. This is a linear function. Now, down here it says, let's do the same thing with Shannon's run. Let's do from 0 to 15 minutes. And let's down here to Shannon, 0 to 15 minutes. From 0 to 15 minutes, okay? In that time frame, she's run 1.5 miles in 15 minutes, right? Okay, so let's put that down. 1.5 miles, this is our rate of change, our rise over our run, our change in y over change in x. 1.5 miles in 15 minutes. Well, to start with, she's running slower than Aleph was, okay? Let's do 15 to 30 minutes. From 15 minutes to 30 minutes. Okay, this is a little bit above that line. So that would be about 2.1, right? So this is 2.1. How much have we gone up? If this is at 2.1, and that's at 1.5, 2.1 minus 1.5 would be 0.6 miles. That would be 0.6 of a mile in 15 minutes. Okay, so let's put that there. 0.6 of a mile in 15 minutes. Okay. Now let's do from 30 to 45 minutes. See, this is not the same rate, so it's not linear. Let's do from 30 to 45 minutes and see what we've got here. From 30 minutes to 45 minutes, okay, that would be at about 2.6, if you look at it. So we're going from about 2.1, which is here, to about 2.6, which is there. 2.6 minus 2.1 would give me 0.5. So that is 0.5 miles in 15 minutes. Okay. Half a mile in 15 minutes. See, she's getting slower as she goes, isn't she? The harder up it is to go up the mountain, her rate is going slower. Okay, let's look at from 45 minutes to 60 minutes. Let's see what her rate would be. She's at 2.6 here. Now we're going to 60 minutes, which is at 3. So about 2.6 to 3. Okay, 3.0 minus 2.6 would be 0.4, 4/10 of a mile in 15 minutes. So now she's running this last little piece. She ran 4/10 of a mile in 15 minutes. Notice how the rate of change is different every place. The rate at which she's running is changing. That is why what you're seeing here is not a linear equation. See how it curves? And this one up here where the rate stayed at 2 miles per 15 minutes is a linear equation because the rate of change is the same everywhere. Let's look at this. It's on the next page. This just gives you a list here of the type things you're seeing. This is a linear function because it forms a line. It is increasing because it goes up. It's going up at a constant rate. This is a nonlinear function because it curves, okay? Does not form a straight line, does not form a line. It is increasing because it's going up. That's a variable rate. This linear function is decreasing because it is going down, okay? And it's linear, so it's linear and decreasing. This one is nonlinear and decreasing because it's not linear, doesn't form a straight line, doesn't have a constant rate, and it's going down. Now let's decide down here whether these two functions are linear or nonlinear. I know it's got it written, but I want to show you how you can tell. If the slope is the same between every point, the change in y over change in x is the same between every xy coordinate pair, then it is linear. So let's check this one. If I check my change in y's, that's 10 minus 7, okay? So that would be 3. This is 1 minus 0. That would be 1. So the slope for that one is 3 over 1, which is 3. M is 3 between those 2 points, okay? Let's try these next 2 points, 110 and 213. 13 minus 10 would give me 3. 2 minus 1 would give me 1. That's 3 over 1. Slope is 3. Okay, now let's try between these 2 points. 16 minus 13 is 3. 3 minus 2 is 1. That's 3 over 1, which is 3. Your slope is 3. And then this one, 19 minus 16 is 3. 4 minus 3 is 1. Okay, that's 3 over 1, which is 3. If my slope is 3, okay, it's the same between every set of points. Therefore, it's linear. Let's try this one here and see how this works. Again, we're trying for the change in y over change in x. I've got 2 minus 0 over 1 minus 0. That is 2 over 1. My slope here would be 2 over 1, which is 2. Okay, so this one's 2. Let's try between these 2 points. 4 minus 2 is 2. 2 minus 1 is 1. That would be 2 over 1, which is 2. So my slope would be 2. See, slope's 2, slope's 2. Let's try this one. 8 minus 4, which is 4, over 3 minus 2, which is 1. That slope would be 4 over 1. And that's definitely not the same. Okay, I've got slope is 2, slope is 2, slope is 2, and then slope is 4. This one is not linear because the slopes are not the same for all of them. Okay, now this is a few pages over. This is example 3 in the Ferris wheel. Lamar and his sister are riding a Ferris wheel at a state fair. Using their watches, they find that it takes 8 seconds for the Ferris wheel to make a complete revolution, go up and down, right? Remember, a Ferris wheel is like a circle. And so they're saying if they start here at the bottom, it takes 8 seconds to go all the way up and back down. That's 8 seconds, okay? And we'll put us some seats here so we can kind of see what we got. There's our Ferris wheel, okay? Now, the graph below represents their distance above the ground with respect to time. Let's look at this. Here's our distance above ground. Here's our time. Now, it takes 8 seconds to go all the way up and then come all the way down. So this is 8 seconds. Go all the way up and all the way down again. This would be another 8 seconds, so that's a total of 16. Go all the way up and all the way down. That's another 8 seconds, so that's a total of 24. All the way up, all the way down, that would be another 8 seconds, which is 32. All the way up, all the way down, and that gets you 40 seconds, right? Okay, let's see what they're asking me here. Is the function represented by the graph linear or nonlinear? Well, this is not linear because look, it goes up and down and up and down. That's definitely not linear. The first question says, is the function represented by the graph linear or nonlinear? It's definitely not linear because it's going up and down and up and down. Okay, so it is nonlinear. Okay, the next question is, where is the function increasing? And what does this mean? Well, let's see. Let's see what we're looking at here. It's increasing. Right here, it's going up. See? The function is increasing between, well, if it's 8 seconds to go up and down, this top's got to be at 4 seconds. So it's increasing between 0 and 4 seconds. Let's see if there's anywhere else that it's increasing, because here it's going down, but here it would be increasing. Let's see, that would be between the 8 seconds and the 12 seconds. If it's an 8-second thing, 4 seconds to go up, 4 seconds to go down. So that would be 8 seconds to 12 seconds when it's going up. Let's see, where else is it going up? Right here. From 16 seconds to 20 seconds, it's going up. Okay, let's see where else it's going up. From 24 seconds to 28 seconds, it's going up. Okay, let's see where else it's going up. From 32 seconds to 36 seconds, it's going up. Okay, now let's see, where's the function decrease? And what does this mean? If it's going up, that means you're on the part of the Ferris wheel where you're going up toward the top, right? Okay, now let's see where it's going down. Here it's going, here it's going down, right? That would be from 4 seconds to 8 seconds, it's going down. So it's decreasing from 4 to 8 seconds. So let's see if there's any other places that's going down. It's decreasing, yeah, right here. Let's see, that would be from 12 seconds to 16 seconds. It's decreasing. Okay, now let's see where else it's decreasing. It's decreasing here from 20 seconds to 24 seconds. It's decreasing. Okay, let's see where else it's decreasing. From 28 seconds to 32 seconds is decreasing. Okay, and let's see where else is decreasing. From 36 seconds to 40 seconds is decreasing. Okay. And what does this next page tell me? It says, how high above the ground is the platform for the passengers to get on the Ferris wheel? Let's go back and look. When they first get on, how high are they up? 5 feet up, right? So that's 5 feet. Based on the graph, how many revolutions does the Ferris wheel complete during the 40-second time interval? Well, let's see. They go up and down, so that's 1. Up and down, that's 2. Up and down, that's 3. Up and down, that's 4. Up and down, that's 5. So 5 times that they go around, okay? Now, what's the diameter of the Ferris wheel? Well, let's look at this. If you're starting 5 feet off the ground, you're starting at 5 feet here. And then when you reach the top, you're at 45 feet. Then what is this distance here? If this is 45 and that's 5, 45 minus 5 would be 40 feet, okay? So the diameter of the Ferris wheel would be 40 feet, all right? We have learned about linear and nonlinear functions. We have learned about increasing and decreasing functions and sections of functions that are increasing and decreasing.